Hello everyone, welcome to the bonus tutorial of the course entitled Simulation of a Mechatronic Machine. In today's tutorial, we will be modeling a simple mechanism, but this time we will model it in Matlab. And if you have no idea uh, about modeling or about coding in Matlab, do not worry, this is the tutorial for you. And we will be modeling simple mechanisms. So as you can see in the animation on your screen, this is a slider crank mechanism. We will not be modeling exactly a slider crank, but I will show you one bar simple mechanism uh, which you can extend it and model it for a slider crank mechanism. So without wasting any time, let's get started. So of course, in today's tutorial, first I just have an introduction, and then most of the modeling part is done in MATLAB. So let's go ahead. So first, our job is to formulate the equations of motion for a planar mechanism using augmented formulation. As you can see, this is the planar mechanism. So what are the requirements for this planar mechanism? Of course, we need a ground, we need gravity, and we need inertial reference system or global coordinate system. So we have this ground, we have this ground, we have this gravity, and this is the inertial reference system. Then we need just one body whose length and mass are L and M, or you can say L1 or M1. Then we have two primitive joints, which are basically sliding constraints. So point A and point B. Point A can move in the horizontal direction and point B can move only in the vertical direction. So we need to formulate the equations of motion. First, I will show you how you can formulate the equation of motion theoretically using MATLAB, and we will be doing symbolic computation. So you understand the value of each symbols or each variable that you use. So let's move on to our MATLAB window. Yes. So once you open your MATLAB, it will look something like this. It's always a good idea to navigate to the folder where you want to save the model. For suppose I am in this path. So this is my current folder, which has no file in it. Uh, just a brief overview about MATLAB. So this is the command window. This is the workspace. This is details about the status of your file. Uh, let's get started with using a M file. So first you go to new and create a script. We will save this script as an M file. So let's say we save as, and in the same folder I name it as main file, for example. And this is a M file where we will be doing all the coding so that you can use the code for later point of view. So just a good modeling practices before you get started. It's always good to give the name of the author. So author is Suraj Jaiswal. Today's date is 14th of October 2020. Just note, like whatever you write after giving this percentage sign is it's the comments. So the code will not take your comments into consideration. That's why it appear in green. And let's say, what are we coding? We are coding simple mechanism. Okay. So before starting any file, I always like to give some lines of code which are needed. So CLC, what does CLC do? You always put a semicolon after each line of code that you do, so that you don't want uh, the values of that line to be to be appearing in the command window. So just the semicolon is used to hide those values from the command window. So what does CLC do in the command window? If for suppose you have anything and if you press CLC, it will just clear the command window. Similarly, clear is another command where if you have anything in the workspace, it will clear everything. And close all is for if you have any other figure or plot window open, it will close all the figures in the plot. So once you have that, let's get back to the presentation. So this is your system, right? Uh, what are the things that you need for modeling? Of course, we will be using augmented formulation, which is also called method of Lagrange multiplier, because it uses this Lagrange multipliers here. But in order to model this, we need generalized coordinates. What are the generalized coordinates in this case? It's the coordinates of the body reference coordinate system. So this is the global or the inertial reference coordinate system, and this is the body reference coordinate system. So we need the location of the body reference coordinate system and the angle of this body. So the rotation of this body with respect to the inertial reference coordinate system, right? And in this case, the body reference coordinate system is located at the center of mass of this body. So this exactly in the center of this bar A, bar AB. So let's say if R1 is the coordinate of this point C, then its x component will be R1x and R1y. And let's say theta 1 is the rotation of this body AB. So let's get back to Matlab. So first I will define symbols. So what are the symbols that I'm defining? Let's say R1, its x component, R1, its y component, and theta 1 for body 1. And just remember to include space between all the variables. Okay. Then you can press 3 period in order to continue the line, continue the code to the next line. You can write all the variables in one line as well. And now we need another symbols such as the derivative of these generalized coordinates. Okay, so dr1x, dr1y, and d theta 1. Okay, that's fine. Now we need another symbols which is mass m1, length m1, and gravity, and we want this value to be real, so we are just defining some limitations for these m1, l1, and g. Correct? Okay, once we have done that, so what are our generalized coordinate? Our generalized coordinate is a column vector such that it has r1x, then I use a semicolon in order to go to the next line, so the next row. uh, You can write it like this. The next one will be r1 minus r1 underscore y, and you can continue, or else you can write it in the same line. It doesn't really matter as far as you have given this semicolon. Correct? So it will basically column vector. If you want to check, if you run the code, and let's say now in the workspace you will whatever you have defined, it will be there in the workspace. And in the command window, if you go and call for q, so q is actually a column vector which has r1x, r1y, and theta 1. Similar, and these are generalized coordinates. Similarly, you can define the time derivative of the generalized coordinates, which will take the form such as this. So dr1x, dr1y, then d theta 1. Okay. So once you have done that, now we will follow the steps in order to define the equation of motion theoretically. So for defining the equation of motion, the first step is to define the mass matrix. If we go back to the slide, this is our mass matrix. Since we have a bar which is very thin and the body reference coordinate system is located at the center of mass, So for that reason, the mass matrix takes a form like this, where this ml square by 12 is the moment of inertia about the center of mass. So we will exactly code this, how we can do that. So capital M can be, now we are writing a matrix such that it's M1, then comma, 0, comma, 0. Okay, you can either uh, include this comma or you can simply remove it. Till the time you have given space, it's fine. But just I do not mess up with things. That's why I give this comma. Then I need to go to the next line. Then 0, comma, and 1, comma, 0. I just like to arrange my matrix in a nice way. 0, comma, 0, comma, and then this time it's M1 into. Okay, I will just copy paste things. And now I need to close my matrix and put a semicolon. So this is my matrix. Just arranging it. Do not worry about, I'm not doing anything new here. Okay, so this is my mass matrix. If you run the code and call for M here, you can see your mass matrix takes the form like this. Okay. Then the next step is constructing the Jacobian. So constructing the Jacobian matrix of the constraint equation. Okay, so how you can do that? In order to have the Jacobian of the constraint equations, you need to first define the constraints. And how you can define the constraints? If we go back to the slide, so what are the constraints here? The constraints here is that the y coordinate of point A will always be 0, right? Because it moves only in the x direction. And the x coordinate of point B will always be 0 because point B always moves in the y direction. So first we will obtain the coordinates of points A and B using this relation. So this relation basically tells you first you need to travel from the inertial reference coordinate system to the body reference coordinate system. So this is R1 here. So R1 here. And then in the body reference coordinate system, you can travel this distance u bar a for point A. So basically this the distance of point A with respect to the body reference coordinate system will be this distance, which is L1 by 2 in the positive direction, if this is x and this is y. And A is of course the rotation matrix of this body, which takes the form, which is of the form like this. If you're not familiar with these content, just let me know, and I will make the relevant material available for you in the comment section of this video. So we will be using this relation in order to define these points and then the constraint equation. So let's say I am using this relation RA is equal to R1 plus AA1 into U bar A. So what is this R1? R1 is basically the X and the Y component of R1. So this one here. So it's again a column vector. Okay. And what is AA? AA1 is basically the rotation matrix of the body. So we can write it like cos of theta 1 then minus sine of theta 1. So exactly the same what I have it over here. I wrote it a while ago, so I just copy paste it here. So cos theta 1 minus sine theta 1, uh, and then in the next row it will be sine theta 1 and cos theta 1. Okay. Now we have defined R1 as well, AA1 as well. We need U bar A. What is U bar A? U bar A is basically the distance. U bar A is basically the distance of point A with respect to the body reference coordinate system. And since our body is very thin, so U bar A can be, it's again a column vector. It will be plus L1 by 2 and 0. So the x component is L1 by 2 and y component is 0. Similarly, we can define point B where you just need to change this U bar since it's the same body. And in this case, U bar B will be minus L1 by 2 and the y component will be 0. So once you have defined these points A and B, now you need to define the constraint equation. If you remember carefully, so now we will be defining the constraint equations. If you remember carefully, I told that the y component of point A will be 0. Before that, if you execute this code and see RA, so RA is again a column vector where x component is the first element and the y component is the second element. And for our constraint equation, which will be constraint equation 1, so the y component is 0. So RA, the second element, is 0. So this can be our first constraint equation. So obviously it is the y component. Similarly, the second constraint equation can be the x component of point B is 0. So this is obviously the x component. Just remember, do not worry about the order of C1 and C2. You can write C1, I mean C1 as this one and C2 as this one. Just understand the logic, okay? The order does not matter here. And then my constraint equation will be obviously two rows, where my first row will be C1, second row will be, and obviously C, the constraint equation C is also a column vector. Okay, now we need to define the Jacobian. So in order to define the Jacobian, so Jacobian CQ as we call it here, CQ will be, there's a function in Matlab in order to find the Jacobian. So Jacobian, we can just call that function. So constraint equation, and with respect to what we want to differentiate it is with respect to the generalized coordinate q, which we defined it a while ago over here. So once we do that, our Jacobian will be ready. If you simulate the file and call for CQ, you can see the Jacobian will take the form such as this. Just remember this, it might be useful for many of you where you just need to where you just have to calculate the Jacobian of some system given in your exam or in your assignment or in your homework. So this is the step that you need to execute carefully. So you don't have to solve everything in pen and paper. You can simply use this simple code and model your system. Let's move forward. So now the third step is to define the vector of generalized force vector. So the third step is constructing generalized force vector. Since in this case there is only gravity and we assume that it acts at the center of mass of the system, center of mass of this body, and the center of mass and the body reference system is at the same location. So for this reason, the the generalized force vector QE takes the form such as this. Okay. Yes. So now we can say QE as 0. It's again a column vector minus m1 into g. G is gravity. We defined it as a symbolic variable. And 0. Okay. Now we have defined this. Our fourth step is constructing quadratic velocity vector. So in order to construct the quadratic velocity vector, in this case, the center of mass coincides with the body reference coordinate system. So for that reason, the quadratic velocity vector is a zero vector. Again, it's a column vector and it is of the form such as this. Remember, the size of this quadratic velocity vector depend upon the size of QE, which depends upon the size of the generalized coordinate, right? So once you have done that, our final step, let's go back to the slide. So if this is the equation of motion, we have defined QE, QV, M, CQ. Obviously, we need to find this Q double dot and lambda. And this, so in order to find them, we are just missing with QC. What is QC? QC is construct, QC is basically constraint vector, vector of constraint equations. So, and QC, as you can see here in the presentation, QC takes the form such as this. I know it's very complicated where there is time dependent term, but in our case, there is no other time dependent term. So the C double T and CQT will be 0. So we are left with only this term over here. So we need to calculate this term. Okay. So first we will calculate the multiplication of Jacobian into the time derivative of generalized coordinate, and then we'll take a Jacobian of that product with respect to generalized coordinate again, and then we'll multiply the entire thing with this time derivative of generalized coordinate, and of course a negative sign. So we will do, let's call intermediate, and as I told you, intermediate can be product of Jacobian and time derivative of generalized coordinate, and then QC will take the form as negative Jacobian of this intermediate thing with respect to the generalized coordinate, and the entire thing will be multiplied to the time derivative of the generalized coordinate. Correct? So once you have defined this, you have all the required components. So the final step is just to combine the matrices and the vectors. And in order to combine the matrices and vectors, if you see the presentation, you have this zero matrix here, and zero matrix, basically we need to define it over here, whose size depends upon the length of the constrained equations. In this case, we have just the length is 2. So for that reason, we can define, say, a variable capital O, which is zeros and 2. So uh, zeros, basically what it does, it forms a square matrix whose row and columns are 2 by 2. And the length, this we have given 2 because it depends upon the length of the constraint equations. Now we will call this part as left hand side and this part as right hand side, and then we can do this inverse. Okay, so let's call left hand side, it's a matrix which has mass matrix, then Jacobian and its transpose. Then in the next line we have Jacobian, and then this is null matrix 0. Okay, so our left hand side is defined. Now we need to define the right hand side. The right hand side, just be very sure with the indentation of this of your code. Sometimes it might be important. So left hand side, basically we have a vector which is QE plus QV, generalized force vector and quadratic velocity vector, and in the next part we have QC, so constraint vectors. Once you have done that, your theoretical equation of motion is ready. So if you simulate the system and if you just want to see how is the left hand side, it takes the form such as this. And if you want to see how is the right hand side, it takes the form such as this. And in the equation of motion, it's done such a way that you can just invert this left hand side and find the solution. Actually, symbolically, we can, so the equation of motion, we can do it here such that there we have RHS and we can do LHS. But remember, for matrix multiplication, this is not how you do the inversion. Inversion is always done using uh, backslash. So, and it is done like this. But this step is not recommended. This line is not recommended. Reason being, you never do the uh, inverse of something which is calculated using symbolic computation, right? If you simulate this, I'll explain you why. If you type this EOM, you see this is the form of your equation of motion, and in this form you have this conjugate, and there might be difficulties most of the times. It's a simple mechanism, so maybe this equation of motion, finding the this in inverse of left hand side is easy, but in many cases it might not work properly. So this line is not recommended. I never told you this. Okay, we do this, but we do this numerically. Numerically it's allowed. So this, so far this is the theoretical point of view. If you want to define your system, uh, I mean, using Matlab and not using pen and paper, this is how it is done. So using very simple symbolic computations, you have defined your entire system. You have defined your equations of motion. And for your exam purpose, this is what is important. But as an additional additional tutorial, like within this video only, I'll explain you how you can simulate your system. So far we have done simulation using Simscape Multibody. You can follow the videos for the other tutorials. But this time we are building everything from scratch, correct? So we would like to see how our system is behaving. So let's go ahead and just I press enter to make some space. So let's go ahead and save these symbolic expressions to files. How we can do that? So in order to convert, so next step is I'll convert the symbolic expressions to file or function handle. This function handle we are not doing at the moment. I'll explain you that as well. So we have this function Matlab function. So by calling this function and then giving your variable and saying it is a type file, and then with what name you want to save it. I want to save it as left hand side file. So it will save this new file in the same folder where you have this main file. So if you simulate this, you see it will appear a LHS underscore file M file. Similarly, we can do that for the right hand side. variable. Okay, so let's simulate this one. Okay, remember to give this semicolon. That's why we are, the answer is saying that it's a function handle. So, okay. Now, once you have done that, all your components in order to define the equation of motion is ready. All we need to do is we need to numerically simulate it, right? In order to do that, first we need to define some input value for our system. So we need to define input data, and we will be using structure array to input the mechanisms parameter. So what is structure array? Structure array is basically you can define any variable as input data, and you can define it as a struct, and uh, parenthesis like this. So now this input data is a variable which is treated as a structure array where you can define different values under the same structure. So let's say I need to define first the gravity, which is 9.81 meter per second square. So I can define this input data dot g. Okay. Next we have the mass and the length of the system. Similarly, we can give the mass as 2 kilogram, length as 1 meter, and we need to define some initial conditions for our system. So the initial condition of what? The initial condition of this generalized coordinate. So what are the generalized coordinates here? It's r1x, r1y, and theta 1. So let's say we define new variable which is r1x, and this is not, so that it represents the value at time t equals to 0, and its unit is, say, suppose meter. Similarly, we can define it for the y component, and similarly we can define theta at time t equals to 0, which is minus pi by 4. Why minus pi by 4? If you see this, this one is oriented in the clockwise direction, so negative sign. And let's say suppose it's 45 degree. So that's why 45 degree is pi by 4 radian. So the unit over here is radian. The angles are always treated in radian in MATLAB. And obviously these are our generalized coordinates, so that time derivative we don't know, so we'll assume it as 0. So time derivative of r1 x naught at time t equals to 0 is 0, and y and theta 1, the time derivative of theta 1, of course. Let's formulate this, all of these variables under one one vector, you can say a column vector, where you have this generalized coordinates and then their derivatives. And of course, this is y naught. So basically, their values at time t equals to 0. Once you have done that, you need to define this t span. I want to simulate the system from 0 to 10 seconds, for example, and I want the time step or the increment to be 0.05. So this is how you write it, and of course it's second. Just try to comment after every line so that at later point of view when you are referring to this code, you don't get confused with what you have coded long time ago. And the last step is solving equations of motion. Okay, how you can do that? In order to do that, first we need to have some integrator settings. I'm not going into the detail, but just options. I'm defining options as an ODE set. We will be using OD45 solver, where I'm saying this stats to be on. You can put it off as well, and the relative tolerance to be 10 to the power minus 7. Of course, the tolerance is for solving the position and the velocity. I mean acceleration and velocity. So you see what we have done in this y naught. Basically, we clubbed generalized coordinates and their derivatives. So q and dq or q dot. So just remember our equation of motion, we will formulate it exactly in the same way so that let me show you in the paint. So if you have, say, it's too broad. So suppose if you have something like velocity and acceleration. I don't know why it is behaving like that. It's too much zoom. Okay. So suppose if you have velocity as this q dot and q double dot as acceleration, then if you integrate this, you can get q, the generalized coordinate, and q dot, the velocity. And that's what we are trying, that's how we are going to solve the equation of motion. So we call this as y, and then this will become dy dt. So we are reducing the second order differential equation into two first order uh, differential equations. That's why we do this transformation, because ODE is capable of solving first order differential equations only. So in order to define ODE function, let me make some space. So before defining ODE, okay, first define ODE. So I'll have an output as time and y, for example, and then ODE 45. First, I need to give an equation handle for the equation of motion. So let's say I will define an equation handle, equation of motion. Okay. Then I need to define the t span. Then I have defined the initial value, which is y naught. Then I have defined the options for the set integrator, and then the input data, right? Just be very careful. Things should be in this order, otherwise it will be difficult. And before this calling, before line 79, you can use tick and talk so that you can see how much time it took in order to simulate your system. So now let's form a equation of motion function handle. What you need to do now is you need to create another function file. So once you create this first, okay, let me copy this equation of motion. The names should be same. So over here, the name of the function should be equation of motion. And let's save it first of all. I'll save it as the same name, equation of motion as written. So it will be same under the same folder. Just be very careful. Don't mix up with the folder thing. And in this one, for the equation of motion, what we need time, we need the y, or let's say the y naught, or y, you can say. And then we need input data, and the output will be the differential of y, so dy or dy dt, as you can call. And this function is basically, you can name it as you like. It's not really important. And over here, first we will call the parameters of the mechanism. So I have already did this coding. So first we will call, and you can remove these ones actually. So call the required mechanism parameter. So we have gravity g, which is inside this input data.g, because you remember here we define g to be under input data dot g. So if you go to input data here, is it there? Okay, uh, let's make a stop here and I'll show you. So if you go to this input data here, you see it has g m1 l1 the way we defined it under a structure. So that's why we are calling this as input data. Similarly, we'll call it for mass and length. Now we need to call for the initial value of theta 1 and differential of theta 1, because we will be needing that. So let's call, so under this y or y naught, because y naught is being input here. So under this y naught or y, so theta is the third element and theta dot is the sixth element. So theta is the third element of y and theta dot is the sixth element of y. Okay. Once you have done that, it's good enough. Now we need to import the function files. So now you'll understand why I just imported theta 1 and theta dot and not any other values, because when you go to the, if you click this left hand side file, just copy this line over here. So you see your function file LHS depends on L1, M1 and theta 1. That's why theta 1. And your RHS function file depends on L1, D theta 1, G M1 and theta 1. Correct? Now once you have done that, let's solve the equation of motion now numerically and using the same trick which I showed you over here. Okay. So once you have done that, so this is of course a q double dot, so ddq, and now my dy is arranged similarly as I showed you here. Okay. So first my velocities and then my accelerations. So what are my velocities? My generalized, not velocity, but the time derivative of the generalized coordinates. So you see this is the time derivative of the generalized coordinate, and this is the double time derivative of the generalized coordinate. This comes from the equation of motion. And this one comes from our initial condition. So this we can arrange it such a way. So the first three components will be the velocities. So y4, y5 and y6 is because over here this is, so this is 1, 2, 3, 4, 5, 6. 4, 5, 6 are the time derivatives of the generalized coordinate. You can write it in one line or you can write it as I am writing. Y6. And then in the DDQ, Q double dot, of course, there will be Lagrange multipliers as well, because we have two constraint equations. So two Lagrange multipliers will be there. So reaction forces from those two joints. And that's why we only need the first three components, which will correspond to the generalized coordinates, the double time derivative of the generalized coordinates. So like this, first, second, and third, and then close this. So once you have defined this function file here of equation of motion, you can simply close it. And now if you just simulate your system, let's simulate, you will see something like successful steps, zero failed attempt, this many functions evaluated. This stats is showing for this ODE solver because we have the stats on. If we make it as off, it will not show. It will just show the elapsed time, which is coming from this TikTok. So the time it took to simulate the entire system for 10 seconds is 0.05 6 seconds, even faster than a blink of eye. Or I don't know how much time does it take to normally for a person to blink the eye. Just a bad joke. So okay, now your system is ready. So this is Y and T. If you actually go to the workspace, if you see this Y here, so you remember this is basically solving for all the time steps, obviously. So the number of rows are the number of time steps, and the columns here are representing, these first three are representing the generalized coordinate, and the last three are representing the time derivative of the generalized coordinate. If you just want to plot, you can go to this plot, select this in new figure, plot. You can see this is how your x, the x-axis of the body reference coordinate system, y-axis, and the theta of the body. But having just these graphs are not really nice. I mean, I'm not very big fan. Of course, it's needed for academic purpose, but for visualization, I actually like to actually see how my system is behaving. Then I have more trust. So let me show you how you can do the animation. You can define the animation yourself, of course. So before that, understand this part, that if you have this system here, if you know the point, the coordinate of point A and the coordinate of point B, and if you just plot these two coordinates, you are actually, and you define a line between these 2 points, then you are actually defining all the points in this body. Okay, so just the extreme points, the end points are always important. You always plot the end point of the body using a line, because this is basically very thin here. So for that reason, I will say first I need to define it in a figure, which can be any, no specific number. And I want to simulate for the entire system, basically for I equals to 1 to length of my t span. So from t equals to 0 to t equals to whatever the length is. Let's see what is the length of t span here, 201. So length of t span is 201. Then we need to define points. Okay, I have it here already. We need to define points A and B for each time step. How we can do that? Okay, it will show an error because we have not, whenever you start a for loop, you should always give a end command like this, then it will be fine. Now, what are your points A and B? You already have it over here, RA and RB, with respect to the generalized, the global reference coordinate system or inertial reference system. Okay, so you can simply save these ones as we did this LHS and RHS. So, converting the symbolic expressions into function handle or function file. So now we have RA, let's say this is RA. Similarly, we have RB and you have RB here. So if you run the file again, it will have this RA and RB. Do not worry about this. So now we can simply go to this RA file and we can copy the first line of the function. And so my RA now is this, where it's say L1. What is L1 here? So L1 is basically input data dot L1. So we can replace this with L1 with input data dot L1. What is R1X? R1X is basically the first component of Y, and in Y, if I just showed you in Y, so this is first component as in the first column, but in I there are so many values. So if you see the size of I is, the size of Y is basically the number of rows is equal to the number of time step. So you need to plot the endpoints of your body at every time step. So say suppose at any time step I, what is your value? So your value can be, for example, I comma the first column or the second column or the third column, depending upon what you want. We want this is basically r1x, r1y, and theta1. So we are interested in only these three. Okay, so my r1x will be basically y, because y we solved it here, and at any time step I, let's say suppose I, and the first column, because that is r1x. Similarly, r1y will be the second column, and theta1 will be the third column, correct? So once you have it in a similar way, you can define rb from here, which takes a similar form as this one. We are almost there, so almost the same parameters. We can replace it with same parameters here. So you have all the points at every time step. Now you just need to plot such that you first plot the x component of both the points. So RA, the x component will be the first one, and the x component of point B as well. Then similar way, just be very careful with the notations that I'm using. So RA, the second component. So now the y components we are plotting. You can find it in Matlab how to use this plot if you are interested, or you can just ask me in the comment section and I'll try to help. Let's say I want the color to be red in color. Okay. Now if you just go ahead and plot your system, it will just show the align because it's showing just the end value, because we need to pause the simulation, right? So pause it, let's say suppose for 0.05. Now if you try to run the simulation, it will keep on changing. Reason being, we don't have our axis fixed. So let's say suppose we fix our axis such that between in the x coordinate from minus 0.5 minus not plus minus 0.5 to 2 meter, and in the y coordinate from minus 0.5, so suppose from 1.5. Okay, now if you simulate the system again, you can see your oh, not like this, wait, just a minute. If you simulate the system again, you can see this is how your system is simulating, and you can see the animation, right? So the point A is only moving in the x direction and point B is moving only in the y direction. Now just to give you some extra thing, if you just press this hold on, you can look at the beauty of plotting your body at every time step for the entire simulation. So I'm holding on for each plot. So this is how the system looks. It actually looks very beautiful, like the 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 workspace or the area that it covers uh, in, in 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 2D space. But this is just, you can play around. You can have many different options to play around with that. So let me go back to my slides and let's see if I have anything extra. Uh, I think, okay, that's the end. I don't have anything else. If you have any question, I would suggest you to better ask me in the comment section, because this email ID may or may not always be there. But for the time being, I have this email ID, so you can email me as well. But it's always good if you are following this video on my YouTube channel. then better to ask me questions on my YouTube channel. And with that, if you like this video, thank you so much, and do share it with people who might be benefited with this video, and have a good day ahead.